Jai Hind to everyone. I myself Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. So today in this complex topic video lecture, we have taken the topic from the subject Digital System Design according to the Technical University AKTU, and here we are going to discuss the topics from the second unit, that is 4-bit parallel adder and 4-bit subtractor. Also we will discuss, which is a really complex topic, that is BCD adder. But these all topics are very important as far as your DSD concept is concerned, also from the point of view of your examination. So this is the circuit for 4-bit parallel subtractor. So here what we can do is, if let's say I have one number, that is A, which is 1100, and another one number is, this is A and this is B. So these two numbers both are of 4 bits. So this is A0, A1, A2, A3. This is B0, B1, B2, B3. So we want to subtract these two numbers. So how we will do it? We will use, initially there is no borrow. When the bits A0 and B0 are concerned, there is no borrow at all. So we can take one half subtractor here in the first block, and if I want, I can put a full subtractor also, and making this input of borrow to be 0. So here I will input my numbers as A0, A1, A2 and A3. The input is 0, 0, 1 and 1, and B0, B1, B2, B3 is 1, 0, 1, 0. Okay. So what the procedure will be like this. The A0 minus B0 will take place, and the borrow will get here. Okay. So the first borrow will propagate to the full subtractor circuit, and the difference will be given by this D0, and that would be 1. Okay. So I have 0 minus 1, so there will be of course one borrow that will go into it, and then the next process will happen, A1 minus B1 minus borrow. Okay. So the difference D1 will come here as 1, and the borrow will propagate to the next full subtractor circuit. Again, if any borrow is there, obviously here if I say 0 minus 1, that cannot be, so here it would have been 1 minus 0, there will be no borrow at all to the third full subtractor. And again here we will do the 1 minus 1 that has gone, giving the borrows to the next two, and then 0 minus 1, obviously there would be 1 borrow, and 2 minus 1 would be there, and 0 minus 0 will be 0. So here the D2 will be, of course there will be no borrow at all, but here the borrow will go like 1, and D2 is 1, and D3 will become obviously as 0. So after that there is no borrow in this case, so that will be 0. So here I can see how we can perform the subtraction using 4-bit numbers, and the for this we can use 4 full subtractor circuits and and 3 full subtractor circuit with 1 half subtractor. So there are 2 options we are having. Now again, this is also another complex topic of digital system design, that is complete logical circuit for performing addition, of 4-bit numbers as well as subtraction of 4-bit numbers. Okay. So the complete circuit will perform either addition or subtraction depending on the value of m. Let us check how this value of m controls the operation of these 4 full adders. So we have taken 4 full adders. This is 1, 2, 3 and 4. So we have 4 full adders, right? And these full adders will perform either subtraction or addition depending on the value of m. So how the m is connected, let us see first that. So this m is input to this carry in, number 1 important point, and another, this m is going to each full adder by using 4 XOR gates. 4 XOR gates, right? So there are 4 XOR gates which are connected to these 4 full adder circuits. Now let us see how the m is, this was all about the connections of m. Now let us see how this m controls the operation addition and subtraction. Just we will clear this and then we will see how it works. So it is very interesting to note the operation of m, right? Let us assume m is equal to 0. Okay. Then we will check this particular circuit will work as adder or this will work as subtractor. Okay. So m is equal to 0, right? If m is equal to 0, then XOR of m with any bit. If m is equal to 0, the 0 and 0 XOR will be 1, right? And if m is equal to 0 and another bit is 1, then XOR of 0 to 1 is what? 1, right? So if it is 1 and 1, then XOR of this is 0, right? So we have one point very clear in our mind. If we do XOR of m with 0, then it becomes 1, the complement of this one. And if I do XOR of this one to 1, then it is complement of this one. So complement, what is the word is? Complement. So I will take, if my m is equal to 0, then XOR of 1 is 1. If my m is equal to 0, XOR of 0 is equal to 0. And if m is equal to 0, and I can say that XOR of 1 is coming out to be 1, and 0 XOR with 0 is equal to 0. Now I have fixed this m to be at 0. Now another case, let us consider another case. If m is equal to 1, then XOR of 0 is equal to 1. If m is equal to 1, then XOR of 1 is equal to 0. So what is the reference which we can take from here? If I fix my value of m to be 0 and I want to make this circuit to work either in adding behavior or in subtracting behavior, then what should I do? Okay, so here let us say we fix m to be 0. If my m is equal to 0 and I am XORing this with 1, the same value is coming out to be there. And here if m is equal to 1, the value is the complement. In this case it is being complemented, the another value is being complemented, and in this case it is same, not complemented. So what the reference we can draw from here? See, let's say I want to make two values to be operated with each other. Please note this particular point, what I have drawn the reference. Just a second. I have two numbers. First is 1, 1, 0, 1. Another one is 0, 0, 0, 1. Okay. I am making this m to be 0. So this will be 0 here. This will be 0 here. This will be 0 here. This will be 0. 0 XOR 0 will be 0. 0 XOR 0 will be 0. 0 XOR 0 will be 0. 0 1 XOR will be 1. So monitor very closely. This bit is being propagated as same. So that means in m is equal to 0, the a naught 1 and 0 being added, and sum will be here, and then carry out will be there. Okay. So 1 and 0 add. So if m is equal to 0, the circuit is behaving like adder circuit, isn't it? Okay. If m is equal to 0, the same is being propagated by the XOR gates, and the circuit, this total circuit is behaving as adder circuit. Now we will see the next case when m is equal to 1, how the circuit behaves. So here 0 and 1 will be added. This will become 1, carry out 0, 1, carry out 0, 0, 0, carry out 0, and 1, 1, 0, it will be 1 like this. So this is how the addition takes place. For m is equal to 0, this circuit will behave as addition circuit. Let us suppose m is equal to 1. Okay. If m is equal to 1, then see what happens. M is equal to 1, we will see what happens next. Right. Now, here 1, this is also 1, this is 1, and this is also 1. Okay. Now XOR of 0 to 1 is 1, XOR of 0 to 1 is 1, XOR of 0 to 1 is 1, and XOR of 1 to 1 is 0. So complement is occurring, complement of all the bits of the second number. That means wherever the complement is involved, the circuit will behave like subtractor. So here since this number has been complemented, and then we are performing the addition operation. So if the operation of addition is taking place and the second number is being complemented, that is nothing but a subtraction method. So for m is equal to 1, this circuit behaves as a subtractor. As a subtractor circuit. Okay. A complete logical circuit capable of adding as well as capable of subtracting. This is how, by using 4 XOR gates and 4 full adder gates, we can make a adder subtractor circuit which is working both ways, as adder as subtractor, depending on the value of m. Don't forget to add the value of m, and don't forget to add the XOR gates. These are 2 key points which we will remember while answering the question of binary adder and subtractor. Next. Now the next topic, as I said, we will study the BCD adder. So let us once again revise the BCD coding system, that is 8421 weighted coding scheme. So here the BCD numbers are defined from 0 to 9, and all these decimal digits are represented by 4-bit BCD codes. 4-bit BCD codes. Okay. So since we have 4 bits, 16 combinations are possible, but only 9 combinations are legal for BCD code. So next remaining 6 numbers from 10 to 15, 10, 11, 12, 13, 14, 15 are known as forbidden codes or illegal codes or invalid codes as far as BCD numbers are concerned. So 1010, 1011, 1100, 1101, 1110 and 4 times 1 are the forbidden codes for BCD numbers. Next, so here it was a brief introduction of BCD numbers, 8421 weighted coding scheme. Now next, since we want to add two BCD numbers, right? So I have two inputs. First is A number, 4-bit number A, and second 4-bit number B. So A is A0, A1, A2, A3 and B is B0, B1, B2, B3, right? And next is C in. The output is C out carry to the next ticket. Z3, Z2, Z1, Z0 are the numbers which will come as some output. Okay. If the numbers are resulting after addition lying between 0 to 9, including 9 and including 0, then it's okay. But if the numbers are after addition coming out to be, let's say, from 10 to 15, including 10 and 15, then there will have a corrective action which will be addition of plus 6. So idea is, then if I add two numbers, A number lying from 0 to 9 and B number lying from 0 to 9, right? If first number A is after addition, let's say output is Z, okay. After addition the output is from 0 to 9, okay. If output is from 10 to 15, not okay, we will add plus 6. We will add plus 6, right? Okay. So in this corrective action we are not applying, but when the result comes out to be 10 to 15, see the maximum and the minimum values which can come, the minimum value after BCD addition will result to 0. Obviously 0 plus 0, 0 is also a BCD number, and the maximum value which can result is 9 plus 9, that is 18. So result will be between 0 to 18. 0 to 9 result is okay, but 10 to 15, 10 to 18 result is not okay. Then we have to add the plus 6, okay, as a corrective procedure. Next. So these two lines, I think these two lines are clear. Now next. So here decimal sum is 0 to 9. We are not applying any corrective action. If the sum output is 10, if it is 11, 12, 13, 14, 15, okay, these are valid numbers. 16, 17, 18 we have added, but one more number we can write as 18. No issues, no problem, we can write it, but let us consider from the valid BCD only from 10 to 15, right? Now coming to the point. 10 number, if I say this is 1010, 11 number which is 1011, okay. So 12 number, this is 0 1 1 0 0 and this is 13 0 1 1 0 1. So this is the output which is coming out, and this is the output which is coming out after plus 6. That means 1 0 1 0, I apply my correction and the output is this one. So this side is the corrective action which I am applying, and this side I have written the invalid BCD code. Invalid BCD code and BCD codes after correction. So this is the final output which we are getting. In all the final outputs, the C out will be obviously 1, as the table suggests. Any number you take from 10 to 15 and apply the correction, there will be a C out definitely. Okay. So again I repeat, this side is nothing but the invalid BCD code I have written, and this side is nothing but after applying the corrective method of adding plus 6 to my invalid code I have written to the right side of this particular table. Okay. So this is how we go. This is 0 1 1 1 1 and 1 0 1 0 1. Okay. So this table is clear, I guess, and if it is clear, then we can move to the next slide. That means what I am going to do, see, from this table I can see either my k is equal to 1, then applying the corrective action. The corrective action is being applied for k is equal to 1. Case 1. I am just drawing the outcomes of this table, and then let us watch this particular table once again, and here I can see my P3 is always 1. My P3 is always 1, but in 2 cases it is going to be 0. So what I can say, if I say कि either my P3 P1 is 1, then the corrective action is being taken, or my P2 P3 is 1, then the corrective action is being taken. Okay. So I have undoubtedly 3 cases where the corrective action will take place. This is either this k is 1, for these 2 cases will cover definitely, and or the P2 P3 multiplication is 1 or P1 P3 multiplication is 1. So case 2, P3 P1 is equal to 1 or P3 P2 is equal to 1. So these are the references which I have taken care for the corrective actions. So this is nothing but P3, P2, P3, P1 and K. So when the binary sum is greater than 1001, we need to obtain a non-valid BCD representative, as I said and explained in the table. The addition of binary 6 is being taking place, and representation also produces an output carry as required. To distinguish them from binary 1000 and 1001, which also have a 1 in the position Z8, we specify further that either Z4 or Z2 must have a 1. Z8 and Z4, Z2 are the meanings, the outcomes which I can represent as P1, P2, P3. So what I will do is I will take two parallel adders. And between these two parallel adders, I will design this logic for corrective action. Please note, this is important. So here I have two 4-bit parallel adders. If the sum is between 0 to 9, this is propagated, same, and if it is 1, then the second will be added to 0, 1, 1, 0, like this. So if this carry is 0, then nothing will be added. If this carry is 1, then 0, 1, 1, 0 will be added, and this is nothing but the S0, S1 and S0 plus S1, S3, and this is K, this is P3, this is P1, and this is P2. Okay. So in the same way we can design this circuit. This is the correction logic which we have made, and it is clear if this carry output is 1, if it is added is output is 1, 0, 1, 1, 0 will be added. If this carry is 0, 0, 0, 0 will be added. So this is the correction logic which is very important. This is the logic for this thing. Let's say sum comes out to be 1, 0, 1, 0. Okay. So here it is 0, here it is 1, this will be 1, and this one is 1, here it is 1, and this 1, 0, 1, 1, for 1, 0, 1, 1 the carry out was 0. So it is 1. Then definitely for 1, 0, 1, 0, 0, 1, 1, 0 will be added, and hence the BCD adder will work.